Good morning, everyone. Today we'll be presenting our mini project titled as a low power 4-bit successive approximation ADC, or in short, SAR ADC. This project was designed using Cadence tools with 180 nanometer CMOS technology and 3.3 volt supply voltage. Our main goal was to design a power efficient SAR ADC, which is a key component used in many data acquisition and digital systems. This project was carried out by our team, Dilshad Mansoori, Shreyash Shamgar, myself, and Aman Yadav. We focus on achieving a design that consumes very low power while maintaining accuracy and speed, making it suitable for low power application like embedded systems and portable devices. Abstract. Abstract. Before we dive into the technical part, our 4-bit SAR ADC was implemented using 180 nanometer CMOS technology, and we achieved a power consumption of just 3.3 milliwatts. This is a significant smaller value than around 50 milliwatts, which was consumed earlier. SAR ADCs are very useful in data acquisition systems such as computer, televisions, and other electronics that operate at the sampling rate about 10 kHz. The main functional block of SAR ADC include a comparator, control logic, and a DAC. The aim was to design and verify these blocks individually, optimize them for power, and then integrate them into efficient system. Reduction to ADCs. It, ADC converters are essentially in almost every modern electronic system. They convert real-world signals like voltage and sound into digital forms, which is then processed by computers and microcontrollers. There are multiple types of ADCs, such as counter type ADC, which is relatively slow, pipeline ADCs, which offer high resolution but are smaller in sampling. Then there are Sigma Delta ADCs, known for the precision but have a low power, low speed. And there are Flash ADCs, which are fast but they occupy a large area and consume more power. Conventional SAR ADC architecture. In a conventional SAR ADC, the operation is based on a binary search algorithm. It uses a special register called the Successive Approximation register, which tries every bit one by one, starting from the most significant bit MSB down to the least significant bit, which is LSB. This process is also known as trial and fit method. The DSC converts the digital code back into an analog voltage, and the comparator checks whether the output is higher or lower than the input signal. Depending on the result, the register adjusts the bit until the closest match is found. Compared to other ADC types, SAR ADCs are much faster than computer counter-based ADCs and simpler than pipeline architectures, which makes them perfect for medium speed and low power applications.
Move on proposed ADC design. Our proposed SAR ADC consists of three key blocks: the control logic, digital to analog converter, and comparator. Each of these blocks was designed and tested separately before being combined into the full ADC system. The control logic handles the bit setting sequence and ensures proper timing of the conversion. The DAC converts digital outputs back to analog voltage for comparison using hardware ladder network, which is simple and power efficient. Finally, the comparator decides whether the DAC output is greater or less than the analog input, guiding the logic for the next bit decision. This modular approach made the design process smoother and allowed us to optimize each block for power efficiency. Now, next is control logic circuitry. The control logic forms the brain of the SAR ADC. It includes a sequencer and code register, which together implement the successive approximation algorithm. Now let's see how it works. The sequencer shifts A1 through a series of flip-flops with every clock pulse. Each sequencer output sets a flip-flop in the code register, starting with the most significant bit. The comparator output then determines if that bit stay at 1 or get reset to 0. This process continues until all bits have been determined, resulting in the final digital output that represents the analog input value. Now let's move on comparator design. The comparator is one of the most important components because it directly affects the ADC speed and accuracy. We design a two-stage CMOS comparator. The first stage is differential amplifier, which amplifies the difference between the input voltage and DC output. The second stage is common source amplifier, which boosts the signal further to produce a clear digital output. Key parameters like offset voltage, delay, and power consumption were optimized during the design. This design achieved low power and fast response, which significantly improved the overall performance of the SAR ADC. Now, next is Aman Yadav, digital to analog converter, continuing with the explanation of this topic.
Talking about digital to analog converter DAC, the DAC converts the digital code generated by SAR logic into corresponding analog voltage. We used an R2R ladder DAC, which is one of the simplest and most area efficient designs. Each bit in the ladder network contributes proportionally to the output voltage. The most significantly bit has the largest weight and the least significant bit the smallest. The DAC output is then sent to a comparator for comparison with the input signal. The accuracy and linearity of the DAC are critical to the overall performance of the ADC, and using the R2R structure helps us maintain both with minimal power usage. Hopping on to simulation result and power consumption, we simulated both the conventional and proposed SAR ADC using Cadence analog tools on the GPDK 180 nanometer CMOS technology. The input voltage and supply was set to 3.3 volts. The results showed that our proposed design consumes only 3.23 milliwatts compared to 50.51 milliwatts consumed by conventional SAR ADC. This represents a huge reduction in power consumption, providing that the proposed approach is far more power efficient. We also compared it with a 45 nanometer design operating at 1 volt, and even then, our design performs competitively in terms of efficiency for the same resolution of 4 bits. To conclude, I would like to say that our project successfully demonstrated a low power 4-bit SAR ADC using 180 nanometer CMOS technology. We achieved a significant power reduction from 50 milliwatt down to just 3.3 milliwatt while maintaining good accuracy and conversion speed. The modular design approach, where we individually design and optimize the comparator DAC and control logic, helps us achieve this efficiency. This type of ADC can be implemented in low power embedded device, IoT sensor, and portable electronics, where both power and energy are major concerns. Thank you.